Hello, kids. I'm going to pick up with the chapter 2 notes, section 1, and we left off at the derivative of a function. And the function we found in example 5 is called the derivative of f at x. So let's just scroll back to that one very quickly. Here's example 5. So we have example 5 is the function x squared plus 1. Find a formula for the slope. And then find the slopes at 2 different points. And one good thing to do is use your graphing calculator and maybe put in y1 is equal to x squared plus 1 and take a look at those points on the graph where you have, where you're saying at x is equal to -1 is the slope -2, or at 2 is the slope 4. So just kind of a good thing to do. And so with this process now, we have a limiting process that will give us the slope of the function. So it's denoted by f prime of x there. Okay, so now you had your different ways to denote the derivative, but in the box we have the derivative or the slope of f. I constantly have you guys saying that over to yourself when you have new terminology. Well, what does it mean? What does it look like? So the derivative of f at x is given by f prime, but I'm thinking, okay, that's the slope of the function at some x value. So the alternative way to say that, remember, is if you have h instead of delta x. So, and again, that we read that f prime of x, we call it f prime. Other forms for the derivative of f of x at f prime are dy dx, it's this one, y prime, that's this one. The derivative, the next one is the derivative with respect to x of f of x. It's kind of the way so it means to take the derivative with respect to x of f of x, and you would get f prime then. And then the last one, I did say that it's not used a lot, but it's still kind of used here and there. And when we read this expression, dy over dx, or some people say dy by dx, but I just read it dy dx. That's the phonics sounding it out kind of way of saying it. Okay, ddx is an operator and means to take the derivative with respect to x. WRT is with respect to. So if we find the derivative of this function, we're going to say f prime of x then is equal to the limit as delta x approaches 0, and I'm going to put in the 3 times the input squared minus 2 times the input minus, I'm going to put a big parenthesis, I'm just going to put in 3x squared minus 2x for my f of x. All of that is then going to be over delta x. I'll fill in just a second. So remember, with f of x plus delta x, this one, it means that we're going to be replacing x with x plus delta x. Okay, so now I can simplify. So I get f prime of x. I'm going to do it all in line. The limit as delta x approaches 0. So I get 3 times x squared plus 2x delta x plus delta x squared minus 2x minus 2 delta x. And then minus 3x squared plus 2x. Okay, distributing the negative sign here and here. Okay, and then let me draw a line, and don't forget we're taking the limit of a fraction here. I'm going to fix this up. I'm going to make that a 3x squared. Well, let's just write it over again. F prime of x is equal to the limit as delta x approaches 0 of 3x squared plus 6x delta x plus 3 delta x squared. And then I have minus 2x minus 2 delta x minus 3x squared plus 2x, and then that's all over delta x. So distributing the 3 to the 3 terms, x squared plus 2x delta x plus x squared. I'm going to cancel terms, 3x squared minus 3x minus 2x plus 2x. So if you notice, all the terms that you have left, here, these terms that you have left remaining all contain a delta x. So you're able to divide that out, and when you do, you will get the limit as delta x approaches 0 of, if you could factor it out, but I'm just going to divide each one of those terms, so I get 6x plus 3 delta x, and then minus 2. Okay, I hope you can see I skipped that step where you will factor the delta x out of those 3 terms that are left, and then I cancel the delta x. So I'm left with the limit as delta x approaches 0 of 6x, that's just 6x, there's no delta x in there, plus 3 times 0 minus 2. So f prime of x is equal to 6x minus 2. And there is your answer for f prime. Okay, that's that one. For example 6, this is our derivative. For the next example, find the derivative of y with respect to t for the function y is equal to 2 over t. So I'm going to make this my function, if you will, f of t. So then I have, this is then the limit as delta t approaches 0. Okay, so I'm just using t instead of then f of t plus delta t minus f of t all over delta t. So that's going to equal, and again, this is f prime of t now that I'm getting. F prime of t is equal to the limit as delta t approaches 0. So I have here my f of t is equal to 2 over t. F of t plus delta t is then going to be 2 over t plus delta t. And that's going to be minus 2 over, because this is f of t now, 2 over t. And that's all over delta t. Okay, so now I'm ready to manipulate this, because if I put in 0 for delta t, I'm just going to get 0 over 0. Okay, so I don't want to do that. So what I'm going to do is I'm going to multiply the top and bottom of this function by the least common denominator, the numerator. So I combine those two, so I would eventually get, then if I multiply by t plus delta t over t plus delta t, so you're multiplying by 1. And then I have to multiply by t over t as well, because they're different denominators. They don't have any common factors. So I'm going to take those and distribute them to the numerator and denominator. So here's what I get. I get this is equal to the limit as delta t approaches 0. So the first fraction becomes 2t. It's just 2t. Minus, then the second fraction becomes 2 times t plus delta t. That's all going to be over t delta t. I'm going to multiply these denominators together, but I'm not going to distribute them. Everything starts to look like t's or pluses, so I want to be careful. So I have t times delta t times the quantity t plus delta t. Okay, so it's t times delta t there. Okay, I'm going to simplify the numerator then. So let me erase this, come back over here. So I have f prime of t is equal to, in the top, let's mess with this a bit, 2t minus delta t. So in the top I get the limit, well, let me write the limit first, of delta t going to 0. And then in the top, so I just get minus delta t. And that's over t times delta t times t plus delta t. So I'm going to cancel those. So that's equal to the limit as delta t approaches 0 of -1 over t times the quantity t plus delta t. Okay, so taking it step by step, you can see where if we look at this all at once, it's like, oh my goodness. So I'm going left to right, starting here, changing the variable to t, and then delta t. And then coming down here for a third step, plugging in the functions. So I didn't do this at first, and I really like to do this. I like to say what the f of t plus delta t is, where it's just going to be 2 over t plus delta t. And this is a perfect example. Is I don't mind working with delta t, but thinking about you guys, I might want to work with an h instead of a delta t here. And there would be less confusion and less t's floating around. But you have to understand delta t is a whole kind of variable. So then after we multiply by the least common denominator to simplify the complex fraction, some of you may combine the numerators and then multiply by the reciprocal of 1 over delta t in this step. Then we end up with this. And then simplifying, here we get negative delta t in the numerator, and then the delta t's cancel, and we end up with this limit. So we end up with -1. We're doing a direct substitution now. -1 times t times the quantity t plus 0, because we're taking the limit as delta t approaches 0. And we end up with f prime, can I get this, fit this in here? F prime of t is equal to -1 over t squared. Let me see if I can make this a little bit smaller. So each step of the way, you kind of like are always kind of saying, where am I? What am I doing? So each step of the way as you go through, 1, 2, 3, 4, 5, 6, 7. So changing to t. Let me do this again. Changing to t, multiplying by the LCD or simplifying the complex fraction, and then still simplifying the numerator. And then once you simplify the numerator, canceling the delta t's, then taking the final limit, where you get this. Okay, so that's all we're doing in that one. We are just getting the expression for delta t with the limiting process. Note, functions are not always continuous, and functions are not differentiable. If they are, though, if they're differentiable, that means you can find the slope, then they're continuous. So these are a few examples where what I'm looking at is indicated on each graph where the function is not differentiable, and note just why. Remember, slope is a limit, so the left-hand limit must equal the right-hand limit. And if it's not, then you don't have slope at that point. So what you're doing here is you're looking at, and you have the reasons here, but at each place in question, here you have a vertical tangent. So at that point, at x is equal to 0, you don't have a slope that's defined. It's undefined. It's positive infinity or negative infinity or something like that. So here, on this one, at x is equal to 0, you have another problem. You have a problem with discontinuity. Okay, so it's not going to be differentiable there everywhere else but these 2 points, vertical tangent and discontinuity. On this one, where there's a cusp, okay, and that is at x is equal to 0, the left-hand limit is different from the right, but not only that, at a cusp, they very often go to infinity. So, well, at a cusp, the tangents do go to infinity, negative infinity or positive infinity. And then for the last one here, where you have the function at x is equal to 0, you have what's called a node, or you have, sometimes we call it a corner. Corner cusp are a little different, but if you notice with the last two, the slope is different from the left and the right. So the slope on the left is not equal to the slope on the right, so then you cannot have the limit as x approaches c of the slope Okay, so you can't have that. You can have the left limit where you have a minus, and you can have the right limit where you have a plus. You're coming from the positive side, but these two are not equal. Okay, so the rest of it, you just have a checkpoint to answer. I wanted to make sure that you had the finishing for this section. Let me flip back. For rates of change, for the derivative, the derivative and the slope of a graph. So this is Alienator out, and I will see you when I see ya. Have a great evening. Take care.